we know everything about lines now. And now we're started to do planes. And the basic idea behind a plane is to find the equation. And the two main things we need to find the equation of a plane are a point and a normal. So let's assume that we have a point. And a normal. And let's call the normal n. I don't know if they use uppercase or lowercase, but I'll use uppercase. And I'll use right now the symbol PT for point. Remember, a point is a vector in standard position pointing to the point. So we can treat it like a point or treat it like a vector. So we have a point and a normal, and I think we've gotten as far as writing this equation where the dot product of the normal vector and a vector that's actually on the plane. And so we took a random vector x, y, z, and then we subtracted the point from it. And then this is supposed to be equal to 0. So this is as far as we got last time. And what I wanted to do is I wanted to play around with this equation and make it look like a vector equation and then make it look like a scalar equation. And so for that, what I could do is identify, I think we did this last time also, the x vector to be the point x, y, z, and then the pt vector to be the point x naught, y naught, z naught. So remember, the x vector was like some generic vector that we had, generic point, we can call it a point that's on the plane. And so what I wanted to do is backtrack on this idea of ABC and call it the normal vector again. And then take a look at how we got this expression, which is the x vector minus the point.
Is the point expressed as a vector?
Yeah. Well, we could put an arrow on top here if you want, but it really is, you know, a point. And this is supposed to be equal to 0. And so if we distribute the n, we can do one of two things. We can distribute the n and leave it like that, or you can distribute the n and then separate these into two different components. But in either case, we've got n dotted with x minus n dotted with pt is equal to 0, or n dotted with x is equal to n dotted with pt. So I'm going to go ahead and box this, and this is the vector equation of the plane. So that's one way to write the plane, and it's not very common to write it this way, but it can be expressed this way, and this would be a good, easy formula to remember. But the more common way to express the equation of the plane is to express it as a scalar equation, which, if we carry out this calculation from here, we can easily come up with that scalar equation. So let's see, n is ABC, x is x, y, z, right? This is equal to ABC dotted with PT, which is x naught, y naught, z naught. It still doesn't look like a scalar, but we know that if we take the dot product of two things, we come up with a scalar, right? So we'll dot them. We got AX, A times X plus B times Y plus C times Z is equal to A times X naught plus B times Y naught plus C times Z naught. Now X, Y, Z, remember, is generic, and X naught, Y naught, Z naught is a specific point. And so with a specific point, we actually would have numbers to put in, and a lot of times people would refer to this as D. Now sometimes they have D on one side, and sometimes they have D on the other side, so it gets a little confusing, but I like to have D on the other side of the equal sign. So the scalar equation that we should be looking for would look something like this. AX plus BY plus CZ is equal to D. Now that makes for an easy retrieval of the normal vector. So if somebody gave you an equation of a plane and asked you what the normal vector was, all you have to do is to look at the coefficients of x, y, and z, and that's exactly what the normal vector is. And I think that is a really, really handy property to be able to use. Not only that, turns out that D is another simple computation. Remember, for an equation of a plane, you need a point and a point and a normal, right? So D just happens to be the dot product of the point and the normal vector. So if you know the point and the normal vector, you can easily come up with this equation without having to go through all that work that we just did. Okay? So let's do an example real quick. Let's say we have a point. What's our point? And we need a normal vector. So we have a point and a normal. We can go through all that work we just did, or we can just say the equation of the plane is going to be given by the normal vector as coefficients of x, y, and z. That would be 2x minus 3y plus 5z is equal to, and then now just take the dot product. 3 times 2 plus 5 times negative 3 plus 9 times 5, and whatever this turns out to be.
So PT is still happening, right?
Yeah. So 6, 30, 45, 21? Sure. $36? Oh, minus 15. I got minus 30 in my head. 5 times 3 isn't 30. 36, you said? Agree? All right. As long as we all agree. Doesn't matter if it's wrong. Except on the test, it does matter if it's wrong. So that's it. That's your equation of a plane. That's all there is to it. I mean, that's the gist of it, but you know, the real story is in the background doing this setup. And the background setup came from the idea that a vector that's on the plane has to be perpendicular to the normal vector, and that's how we got the dot product to equal to 0. All right. So now, intersection and distances are interesting things to discuss. Let's start with a distance. Let's figure out the distance from a point to a plane. So let's say, let's do an actual example, and then I'll draw some stuff on the screen. Let's say we had a point. What's our point?
3, 4, 5.
And then what's our plane? So how do
6, 7, 8.
what? 7x plus 9y minus 2z 15. So this would be a good example. Thanks, Oscar. This is a good example of a plane. So this is a good sign that when I ask you to give me an example of a plane, you know exactly how to say it. You don't say 7 plus 3x. No, that's not a plane. So something like this would be a plane. Okay? All right, so let's find a distance between the point and the plane. Maybe I should have went intersection first. Let's do distance. Let's try it. So let's randomly draw a plane over here and pretend that this is our plane. And then let's say this is our point. Our point is up here somewhere. And what we want to do is when we're looking for distances, usually we're interested in the shortest distance, which is going to be this perpendicular distance between the point and the plane. So if we can find this point, that would be great, and we can find a distance formula, right? I don't know if we can find that point. Yeah?
So I think the way you do this one is like you find any point on the plane.
Any point on the plane.
And then you project that onto the normal vector for the plane.
And you project that onto the normal vector of the plane. So let's draw the normal vector to the plane. That sounds like a good sign, right? Because the perpendicular distance has to be the same direction as the normal vector. It's perpendicular, so I think it's a good assumption that the normal vector will be involved in this calculation. And you're going to project, so that was close. You're going to project what onto the normal vector?
The distance between the point, that 3, 4, 5 or whatever,
Uh-huh.
and I guess like
Any point on the plane.
on your plane.
Okay, so this looks like it's the same distance. I didn't mean to make it look that way. So I'm going to change my normal vector just to make it longer or shorter.
Oh, maybe
Now you got it.
version of it?
It doesn't have to be unit normal.
Don't have to?
No.
Oh, so then.
It's pretty much what you said.
Okay.
Except the wording is probably a little bit different. So, what we would be looking for would be if we drew a vector from any random point on the plane to that point that we know of, and then project that onto this normal vector, then we could possibly get that length. Okay? So let's see. The normal, remember, a vector can be moved around, and it would still, as long as it has the same magnitude and direction, it's still going to be the normal vector, right? So we can move it around, and probably the best place to put this in is right at the tail of that point of projection. So I'll do that in a minute, but maybe I'll make a couple of extra copies of these, of these vectors, so I can feel free to move it around a little bit. So this is not quite the projection story that we have. We project onto the normal. So if we take these two vectors and maybe twist it a little bit so that we can see this projection going down, that's more how we learned the projection idea. And so if we imagine extending this, because I made the normal a little too short, if you imagine extending that and then looking at this distance over here, nope, sorry. This is the distance that we would be looking at. So you have the projection, and then here we're looking for this distance right here. Turns out that is this distance that we were looking for the plane. Okay? So, random point, any point should work. Let's call it as random as possible. Let's call it x naught, y naught, z naught, because we've kind of known that x naught, y naught, z naught is on the plane already, right? And then this is our normal vector. ABC. Yeah, I don't know if I wanted to use the actual values. I think maybe instead of doing this example, maybe I wanted to go general first so we can come up with a formula, and then we can just plug and chug. Maybe I should have thought about that and saved this example for later. So let's move this example aside for now. And let's work with this. Okay, so now since we are working with this, we have to actually identify this new point as some, instead of 3, 4, 5, let's make it random point x1 this time, x1, y1, z1. So x naught, y naught, z naught is on the plane. x1, y1, z1 is not on the plane, and we're trying to find a distance from the plane to that point. So anyways, we're looking for this length over here, which is a component projection. So sometimes we call it scalar projection because all we care about is the length of that projected vector, not the actual vector itself. And if you guys remember this, the formula for scalar projection, you're projecting component, projecting this green vector. We don't have a name for the green vector. Let's call it V. The green vector is the subtraction, the difference of x1, y1, z1, and x0, y0, z0. So the component projection of V, and we're projecting it onto N. And I don't know if you guys remember the formula, but the formula had a dot product at least. That's what I remember. And then it's divided by a magnitude of either N or V. That one's a little tougher to remember. But it turns out to be the magnitude of what you're projecting onto. You're projecting onto. So you're projecting onto N. So we're looking at dividing by the magnitude of N. That looks like a V. What if I just... So remember the magnitude is like the absolute value. All right? So that's our key, that's our idea. And if we find this, that's exactly the length that we're looking for. So the component projection is our key. So what is our component projection? Well, we got some values here. We got x naughts, y naughts, z naughts, x1, y1, z1, and a, b, c. So V, let's establish what V is equal to. V is the difference between those 2 points, head minus tail. Actually, it doesn't matter which one the head is, which one the tail is, because we're going to take the absolute value. So it'll be x1 minus x naught, y1 minus y naught, z1 minus z naught. That's your V vector. So I'll put that over here just to get it ready. And then our N vector we know is ABC. And then the magnitude of N is the length of N, so that's the square root of A squared plus B squared plus C squared. And since we are looking for a length, just to clear the air here, we might get a negative because sometimes the dot product is negative if your angle is bigger than, what is it, 180 degrees. So in those cases, we just want to make sure that we account for that and put absolute value. Yes? It doesn't need to, because we don't care about the vector length. I mean, we don't care about the vector itself. We care just about the length of this thing that we're looking for. All right, let's work this out. Just the whole idea behind working this out is to come up with a nice, neat formula. So I'm going to distribute or take the dot product of the A, B, and C. A dotted with x naught minus, or x1 minus x naught, plus B dotted with y1 minus y naught, plus C dotted with z1 minus z naught. That's the whole numerator, and then the denominator stays the same. And then we could separate these to ax1 plus by1 plus cz1 minus ax0 plus b minus so I distributed the A, B's, and C's, and then I regrouped them so I have all the x1, y1, z1 together, x0, y0, z0 together, and so it's separated like this.
Why is there a plus C?
Oh, that's because it's a typo. So x1, y1, z1 came from the point, and then x0, y0, z0 is a point on the plane. Now the fact that we have a point on the plane and we're dotting that with the normal tells us that that should be equal to what? No. The dot product, remember, is a scalar value. It's what? No, not quite. All right, here's what I want to do. The distance, I want to write the final formula. I know that the denominator is going to be the same. The numerator has an ax1 plus by1 plus cz1. And then now if I take out the negative sign over here for all three of these, I have ax0 plus by0 plus cz0, where x0, y0, z0 is a point on the plane, and a is a normal. What? D. That's the D from our equation of the plane. Okay, this is our equation of the plane. Well, oh, I'm running out of battery. I'm not plugged in. Let's do this as an example. Say it again, Danny. D is a dot product of the point and the normal vector. The point on the plane and the normal vector, which is the other side of. So if we have the actual equation of the plane, it would be this number. So let's do this. Now that we have the formula, our distance formula is going to be easy. So our A, B, C are the coefficients of the x, y, z, and our x1, y1, z1 would be those points, the components of the points. And then our D is equal to 15. So the distance in this problem is going to equal to the magnitude of A times 3. So I'm going to put actual numbers here. 7 times 3 plus B is 9. Y1 is 4. C is negative 2. Z1 is 5. Minus the D, this is where the 15 comes in, divided by the square root of 7 squared plus 9 squared plus negative 2 squared. Okay? All right, so you probably want to work that out, punch it in a calculator, get a number, simplify. Okay, so I want us to be pretty proficient about being able to find equations of lines and planes. So I have a worksheet here for you guys. All right, find an equation with 3 planes. You got 3 points on the plane. Here are your points. Find 2 vectors connecting the 3 points. You cross them, and then you get the normal vector. So here are the 2 vectors. We cross them, and we got negative 10, negative 6, negative 26, and negative 6. They're all even, so you can decide to subtract out. They're all negative, too, so you can decide to factor that out. And remember, the normal vector, all we care about the normal vector is the direction. So it doesn't matter if this is shorter, longer, if it's pointing in the other direction, it doesn't matter as long as it's perpendicular. So we can leave it like this, or we can divide out if we want to do some simpler computation. Yeah? The I, J, K can be written with a hat if you want, because they're all unit vectors. Or you can just really rewrite this whole thing as negative 10, negative 26, negative 6. Or you can modify this. You can modify the new normal. Isn't that a show? By taking out a negative 2. And so take out a negative 2, this becomes a positive 5, this becomes a positive 13, this becomes a positive 3. So this would be another normal that's probably pointing in the other direction, that's a little shorter because it's half as long. It doesn't matter. But the idea is that if I reduce this like this, then it would be easier to find my plane.
You can just divide it by 2.
Yeah, because all you care about for the normal vector is the direction. You don't care about the magnitude. Or, if it's going positive or negative.
Going down, and
That-
divided by negative 2, we're going up, and we want it to go up.
Yeah.
Okay.
Not that we want to, but it would just make things easier.
Make things
Yeah. Okay, so let's use a formula. AX, so that's 5x, and 13y, and 3z. And then the D, remember, is the dot product between the normal and the point. And what's neat about this is that if I take the dot product of the first one, so that would be 5 times 1 plus 0 times 13 plus 2 times 3. So this is 5 plus 6 is 11. Is that right? 11? Then that would be your answer. Now, this would work with any point on the plane, right? So instead of choosing 1, 0, 2, maybe we choose negative 3, 2, 0. So if we take negative 3, 2, 0, and then we dot this with the normal vector 5, 13, 3, then this should be negative 15 plus 26 plus 0, which is the same number, right? It should be like that if it is in fact on the plane, and then you could do the same for 2, 1, negative 4. You'll see that if you dot 2, 1, negative 4 with a normal vector, that you're also going to get 11. All right, so we didn't get to too many intersection problems. I wanted to deal with intersections of a line and a plane, two planes, and stuff like that. So we'll talk a little bit about that tomorrow. But I do really want you to do the basics. So this worksheet, compared to the last worksheet I gave you, this worksheet is supposed to be a little bit simpler. The worksheet that I gave you last time had like multiple layers and levels. So I'm trying to rework the way I give worksheets so that it'll be something quick, and then it's something that needs to be one of those like arsenal things to help prepare for those longer types of problems. Okay? So make sure you know how to do each problem on this worksheet, at least number 1 and number 2. Get really comfortable with it so that you can answer the more complicated problems that I'm going to give you on exams. Okay.